Welcome everyone. Today is Wednesday, July 20th, 2011. This webinar will be covering function block protocol. So we'll start off with a PowerPoint presentation going over some of the basics, and then we'll take a look at a demo application I've written that goes over the function block protocol, and we'll review also how the code functions. So this presentation, as I mentioned, it's going to be going over the physical layers. The ASCII protocol itself is open definable. So what that means is that you will be able to make our PLC essentially talk to any device that's out on the market there that supports sending ASCII strings. Some of the more common devices are frequency converters, barcoders, barcode readers, printers. There's a lot of different devices that you can actually use. So essentially, as long as it talks strings, we'll be able to go ahead and communicate with that device, sending the strings back and forth. So the function block protocol, it allows you to send and receive these ASCII string messages. So the physical layers that we support are over serial, whether that's RS-232 or RS-485, and also over Ethernet. So in the webinar today, we're just going to be going over the serial portion, but the same principles apply whether or not you're doing Ethernet or serial. They're essentially the same. So if you're familiar with understanding how the serial function block protocol works, it won't be a problem to understand how to do the Ethernet. So you can see in these graphics here, it's just a pinout of the RS-232. This is what the port on the controller. RS-232 is typically just 4 wires. You have a transmit and a receive, and also just 2 grounds is all that's being used. The inside 4 pins on the side of your PLC. And also to the right is a graphic of the default socket and port configuration as well if you're using Ethernet. But both of these are able to be changed, whatever socket you want to use or whatever port you want to use, that's all openly configurable in the software as well. So you have 4 different sockets you can use. And if you have more questions about Ethernet in general, we do also have a webinar that we have done previously covering more details on Ethernet in general. But the function block protocol, the main point is that you can use that over serial or Ethernet. Both physical layers are supported for our function block protocol. So what is ASCII actually? ASCII is the American Standard Code for Information Interchange, and it's the basis for all the strings that will be transferred. So when we're sending a string back and forth, say hi or hello, that string is actually in ASCII characters, and you can see a chart here. I just got it from lookuptables.com, but this chart is also available in our help file as well. The chart really, it shows you the conversion from going from the ASCII characters to what their decimal representation may be or what their hexadecimal representation may be. So for example, if you have the letter, say the letter L, the letter L is actually a 76 in decimal or a 4C in hex. So whenever you send the string L, it will be represented as a 76 as far as the controller is concerned, a 76 decimal or a 4C in hex. So when you build longer words, if you say send the string hi, it will send first the H, the ASCII H as a 72, and then it will send the I, which is a 73 decimal, assuming you're using capital letters is what it's shown here. There's also different ASCII codes for lowercase or uppercase characters, but say here you're sending the word hi, it would be the 72 and the 73. So it's really just showing you how they convert, and most of the times you don't even really have to worry about this, but it's just good to understand where the ASCII equivalent decimal and hexadecimal do come from. But for the most part, the controller will take care of all this formatting for you, and all you really need to do is just type in the actual strings that you want to send back and forth, which we'll We'll look at it in a little bit, but as I mentioned, it's a good idea to know where these come from and how they translate back and forth between the decimal, hexadecimal, and the ASCII character representation. So just a little bit more explained about the bits and the bytes. One ASCII character, so we just looked at the ASCII character chart. One ASCII character is equivalent to 1 byte as far as memory utilization and memory usage is concerned. So you have 8 bits in a byte. That's just standard memory allocation. It's not anything specific to Unitronics. That's just how the standards are defined for different memory capacities and storages. So you have 8 bits in 1 byte. So let's say in the slide here, the character G, that occupies 1 byte of memory. So whenever you send a G, it's going to take 1 byte of memory, which is also equal to 8 bits. So how that translates to our different registers or our operands that we have to work with is also explained here. We have memory integers are our standard types of operands or registers that you're going to be using. A memory integer is a 16-bit register. It's a signed 16-bit register, but the signing isn't really important here. It's a 16-bit register. So that means we can, in essence, hold 2 ASCII characters. It's 16 bits, which is equivalent to 2 bytes. Each character is 1 byte. Therefore, you can have 2 ASCII characters be held inside a single memory integer register. So we saw the G takes up 1 byte. If we want to send the word go, you would also have to include the O character, and you would have the G and the O each representing 1 byte. Both of those can be held inside a single memory integer. So you have your 2 characters inside a single memory integer. Now, we also have larger types of operands to work with, whether it's a memory long or a double word. Both the memory longs and the double words, the MLs, the DWs, those are both 32-bit registers. Therefore, it's 32 bits, which is equivalent to 4 bytes. Each ASCII character is a single byte. Therefore, you can have 4 ASCII characters stored inside a long or a double word register. And the graphic just helps you understand it here once more. If you have the word July, you can actually fit all 4 of those ASCII characters inside a single memory long or inside a single double word. The J is 1 byte, the U is 1 byte, the L is 1 byte, and the Y is 1 byte. Those 4 bytes are all contained inside a single memory integer. Now, what happens if you have a string that's longer than that? Say you want to say, go to the beach. You would have still, the bytes would be stored inside the memory integers, and you would just take advantage of a vector of memory integers. A vector, or it's also similar to an array, it's just stored sequentially. So if you have, it's starting in memory integer 0 and it's a long string, the first 2 bytes would be in MI0, the next 2 bytes or 2 characters, however you want to say it, would be in MI1, the next in MI3, so on and so forth. If you have a larger string, essentially, you would just use multiple memory integers or multiple memory longs. They start at the first starting address, and it just goes after that consecutively in what we call a vector. So as far as the actual function blocks that we use, you'll see there's a configuration where we define the port that we want to use. So if we're using serial and you have 2 or 3 available serial ports on your PLC, you need to specify which actual port you're going to be using for this protocol. So you define the port in the configuration. Also, there's a status. The scan block allows you to define the message structure. The send also defines your message structure. So you have to basically configure the strings you want to receive and the strings you want to send. You do that with the scan and the send block. We'll look at these all in more detail with the actual example program, but just a brief overview is on this slide. Copy buffer contents. It allows you to store the message that has just been received. It's held in a buffer. You can store that to some additional vector of operand. So if you want to also, say, backup the strings that you're receiving to the data table, you can store those in, say, MI1000 and up, and just copy those to the data table after. But the main idea of the buffer copy contents is that it takes the received message and goes and stores it in wherever you want some user-defined section of memory that's later accessible to do whatever you want to do, whether that's storing it or analyzing it, doing some logic operations based on it. It allows you to also take out the entire buffer contents and store it in some extra space. And reset buffer is pretty self-explanatory. It will clear the contents. It'll clear out the buffer register. The buffer is internal memory, but this reset buffer will clear it. It's a good idea to clear this or reset this buffer every time you receive a message, and we'll look at that in the actual program as well. And that's it for the PowerPoint. We'll take a look at an example program I've written now. We'll do a demo first, and then we will take a look at how it actually works. So let me open up VisiLogic. This is the application here. I'm going to go into online test mode so you guys can see what I'm looking at on my screen. I'll pull up the remote access. Once again, that's just online test mode with the glasses. Hit the F9 key. And then you can also open up remote access. And I'll make it a little bit larger. Okay, so this function block protocol communications application is downloaded to just a V570 I have sitting on my desk right now. So with this application, I'll briefly explain, it's set up so that it can receive a string that's sent to it, and it also sends out a string that says test message. That was the objective of this example program. So you could, in essence, hook up your barcode scanner or your frequency driver, whatever type of device hooks up and sends ASCII strings. You could connect to this application as a test, receive the message, it's going to display it on the screen. For example purposes, I'm going to be using a terminal program to emulate my barcode scanner or my printer, say. I'll open that up so you can see. You can use any type of terminal program really that you like. This program Hercules, it's a piece of freeware. You can see the website is on the bottom right-hand portion of the software. It's just a piece of freeware. You can go download it, hw-group.com. It's like a hyperterminal, which is also included with Windows. However, it's a little bit easier to use because you don't need to set up any sort of macros like you would in hyperterminal. Whenever you type a string in the send block that's blinking right now, it will automatically generate a macro for you and send that out. So it's just a little bit easier to use, a little bit easier for debugging. That's why we use it in our training classes and also recommend that customers use this freeware as well. But the things you need to set up in the program, we're just going to be on the serial tab right now, but I'll mention briefly there is also a TCP client and server option, so it's a really good tool if you're doing any sort of Ethernet function block protocol over Ethernet, or even a Modbus or any type of Ethernet communications. You can use this as a terminal emulator as well. But right now we're just concerned with the serial tab. So there's a received and sent data window. It's going to echo back what we send and what we receive in this white window in the middle. Things you do need to define before you can start. They will be on the right-hand side under serial, the name. So this is where you pick the virtual COM port. So if you have a USB adapter, say it assigns your USB adapter to COM5 or COM6, you need to pick from the drop-down whatever COM port your computer happens to be using. Mine is just using COM1. It's a little bit simpler, but again, you just pick whatever virtual COM port Windows assigns from, say, your USB adapter, whatever port you usually communicate to the controller with. That's what we're defining here. The baud rate, again, there's a bunch of different options, the standard rates. You just need to make sure that you match this baud rate speed to whatever your VisiLogic program is set up to, and in the real world, whatever your printer talks at or whatever your barcode scanner talks at, you need to make sure you match the correct baud rate. For example, if you do not match the correct baud rate, you'll see it'll look like gibberish, sending back and forth. The characters won't make sense. They'll be strange uppercase, lowercase symbols. That's one indication when you're trying to troubleshoot. If you don't have the proper baud rate, the message won't make sense, essentially. So what you need to do, main point, is set the correct baud rate. I happen to be using 9600 in this demo application, so I'll set that at 9600. And same is true for the rest of the control characters or the header characters, the data, size, parity, handshake. The standard is 8, none, and 1. I just have this configured, we'll see in a minute, to match the COM port initialization. But the terminal program lets you set up to be able to match whatever your device is set for. So in this case, the PLC, real world, it could be whatever your third-party device is set up to operate at. So I have this matched to my Physiologic program. I'm going to click the Open button. You'll see it gives me feedback. It says my serial COM port 1 has been opened. So if I click the Send Test message, it minimized my Hercules, but you can see Send Test message now pops up on the screen here. So I can also tap it again. You'll see it's sending multiple test messages, and that's just echoing back on the screen if I want to. So that was sending a message from the PLC to the terminal program. So that would be sending, say, a message from the PLC to your printer. I would print out the text message test. But I can also go in the reverse direction. So I'll type in hello. Now, once I click the send button in Hercules, you should see the message will pop up on the PLC screen in the light blue window. So I'm going to click send, and the message hello pops up. You can define a bunch of different messages to send. I'll type webinar and hit send, and the screen updates to say webinar. So that's really the main idea of this example program. It's sending the messages back and forth. Using a terminal emulator program is a good way to test your communications. If you, say, don't have your third-party device readily available to hook up to the PLC, but you do know the string structure, you can use a terminal program in the meantime to emulate that third-party device and get your coding going, say, before you actually have the device you're trying to communicate with. It's really just a good test tool for debugging and getting your program up and running. I guess the only other thing I didn't mention on this example program, but you probably noticed there's just a counter. So whenever I hit the send test message button, that counter is incrementing. You see 13, 14, 15. We'll look at that after, but it's really just keeping a count of how many messages that I've sent from the PLC. You can also do the exact same thing for the number of received messages. I just happen to not have it on the screen here. But you can set up the same sort of counter to see how many messages have been received or how many messages have been sent. So that's really what I wanted to show for the demo portion. So I'll close my COM port, and we will take a look at how the code is set up. Okay, so in the latter portion, the best programming practice is to always have a system bit 2 power-up bit with all your essential communication parameters or your one-time configurations. The SB2 is a one-time power-up bit. This bit is only active the first time the controller powers up, a single scan, and a single scan activation is all you really need for any of the communication configurations or any of the COM port definitions. So first we just have a PLC name, gave it the name PLC. Good programming practice to have a PLC name. It's found under the COM menu, set PLC name. I also have a COM port initialization, once again found under the COM menu, COM port, and init for initialize. So this COM initialization, we'll open that up. And you can see I've defined my COM1. Now it's important to point out the COM1 here, this is referring to the physical port that is on the PLC. So I happen to be using, you saw in Hercules COM1, that was referring to my PC. This COM port is referring to the PLC's COM port. So you'll notice when I drop down, it's COM1, 2, and 3. There's only 3 available COM ports because the maximum number of COM ports you can have on, say, a 570 or a 1040 is 3 COM ports, 3 available ports. It comes with 2. You can add 1 on. So the main point is that this COM port is referring to the physical COM port on the side of the PLC. There's also options for CAN when you're defining the CAN bus port, which was covered in an earlier webinar as well. But right now I'm just using the first COM port on the side of my PLC, the one on the top left-hand side of my 570. So I've picked COM1. Again, the data bits, parity, stop bits, these are all something you'd want to match to your actual third-party device that you're trying to communicate with. When you're just using a terminal program, it can really be whatever you want. I just left it on the default. 8, 9, and 1 is pretty standard. Once again, the baud rate I defined at 9600. The timeout is also half a second. And really the only other important thing is under the drop-down here, the standard RS-232 or 485. We do support serial communications under either. You need to make sure you define your PLC port to be the correct one that you want to use, and it's also important to mention as well, when you change the COM ports, you need to make sure you change the jumper settings inside the controller. So it's software defined, and yet it is also hardware defined as well. So they're actually dip switches, not jumpers, but they're dip switches that you need to define for RS-232 or 485. We support both of those physical mediums over the serial communications. So I will close out. Now the protocol config block, that's found under the menu FBs for function blocks and protocol. We saw a screenshot of this in the PowerPoint earlier. There's also the protocol TCP is right below. If you're using the Ethernet option, we're just going to be using serial right now. So I grabbed the protocol config block. This is where you'll see the scan and the reset, all the things that we talked about before, and you can see in the ladder are under this FB menu protocol. So if I open up the protocol config, you'll see there's not a whole lot to define. You can give it a name. The name is arbitrary, really. It just helps you keep track if you have multiple COM ports going and multiple devices hooked up. It just gives you a little bit ease of naming convention in your actual code. So I just happen to call it ASCII. Main thing is to pick the COM port. So once again, you have the option of 1, 2, or 3. We're using COM1. Generally, you want to match the COM port you pick here with your COM port initialization. It's really just the COM port that's going to be hooked up with the device is hooked up that you want to send messages to and from. So there's also a function in progress and a status. So these two options, you define the next available memory bit or next available memory integer. What do they do? The function in progress, if you're currently, say, sending a message out of the port or you're currently receiving a message, you can only do one thing at a time on a single serial port. So you don't want to be trying to send a message while you're already receiving one. It won't go through. You can only do one thing at a time. So we have this function in progress bit which monitors whether or not a message is currently being sent out or currently being received, and you can put a kind of like a fail-safe into your ladder logic to monitor that bit to make sure that nothing is currently in progress while you're trying to send. That's what we have, and you can see net5 here. We're making use of that. And then there's also a status as well. So the status, you assign it to a memory integer, and the status is going to hold a message number, essentially a code, which will help you with debugging. Now, if you want to know what that message actually means, you can always just click the help button in our function blocks, and it will bring you right to the correct portion of the help file for that function block. So I'm going to click on configuration, and you'll see it explains what each parameter inside this protocol config does, like I just mentioned, but the status, an error has occurred. So I want to check the protocol status messages. Generally, you'll want to see a 0. A 0 in almost all our function blocks means no error. But if you have a 1, 2, 3, 4, the chart here goes over what each of those potential problems, what those error codes actually mean. You can go back and reference this. You can also put in your software, you can have, if the memory integer for the status equals a 3, give some feedback on the screen. There's a lot of different things you can use the status for. Besides debugging, you can give user feedback live on the controller screen as well using that status message. And all of our status messages, once again, are available in the help file documenting what the different values correlate to. So that's all we really need to do to define the protocol, to set up the COM port, set up the config so that the COM port is set to function on this ASCII protocol. One last thing in net 1 is just a set bit of MB3. Really, what I'm doing here is, as long as the COM port was successfully initialized and set up to do the ASCII protocol, we're going to set a bit, which therefore enables our scan. So really, we're just saying we're not going to be scanning for messages unless everything was set up properly. So if everything was set up properly, we're going to make MB3 high, we're going to set it, and therefore in net 2, we're going to essentially enable the scan block. So I'm going to open up the protocol scan. And you can see this is where the message structure is able to be defined. So there's a couple different ways you can set up the protocol scan block. Generally, you'll want to match this so that it's the same as the messages that your third-party device is sending to our controllers. So there's two kind of main ways you can do that. What we've done in this particular application, just for ease of use, is that we've defined one long variable. So essentially, any type of string that you send, any type of string that you throw at the controller, we're going to be able to read. And we're doing that with what's called a variable. So you'll notice that this is defined as a variable by the fact that there's a string of ones and it has a gray highlighting behind it. You can see after that is white is empty. So this is a variable because it has the string of ones and also that it has the gray highlighting behind it. The gray highlighting is really what makes it a variable. So what is actually a variable? A variable allows you to receive any type of message that's sent in. It doesn't have to be static text. For example, if I type in hello after, you can see now that has a white background with the black text. That means that it is a static string, so you would have to actually send to the controller hello with a capital H and the rest lowercase for it to be able to receive that message. Really, the variable gives you more options if you're not sure about the type of string that's going to be sent, or the type of string is always going to be different. Using one big variable and parsing out the details later on is generally good practice that you can follow. So as far as actually getting this variable into the scan block, the button for that is this yellow Create Edit New Variable. If I click that, I'll open it up here just so we can see. That's what I clicked to add this string of ones here as a variable. So under the variable, there's a couple different options. There's a numeric, a stream, and a checksum. So we'll look at the numeric tab first. It was previously set up as a stream, but going over the numeric allows you a couple of different options. You can have a decimal as ASCII fixed length, decimal ASCII no fixed length, and hex as ASCII. So what those actually mean is if you're always going to be sending a number that's, say, 4 digits long, you can go ahead and do the fixed length. But if the number could be 100, or it could be 5, or it could be 50, those are all different length characters. So if you have different length numbers you're going to be sending, really the no fixed length is the best option to select. So the type of decimal we're going to be sending, and you need to make sure, the main thing is to give it a link property. Same is true for the stream and also the numeric. The link is where the value that's sent into the controller, that string that's being sent from your third-party device, the link is what allows you to define where it's actually going to be stored in the memory section of the controller. So I'm sending a numeric. It's going to be storing that numeric inside my MI20. So that allows us to send a number, it's going to save it, store it in that MI20. You have the option of defining a prefix, so if it's a negative number only, or a positive negative, or no prefix, those are just more options you can define. Also a decimal point, if you're going to be sending 100.2, what you'd have to do is assign a decimal place, so it would say place that decimal place three characters over. Now the way you do that, you can't just punch in a 3 here if you know you're going to have 3 spaces and then a decimal. It doesn't allow you to have a constant, so what you need to do is pick a memory integer, say MI2000, and give it a power up. So if I have a 3 as a power up condition and MI2000, it's going to place a decimal point 3 places over. So really MI2000 is going to have a value of 3. That means the decimal point number is going to be shifted over 3. The function block protocol will automatically add that for you. And once again, that number will be stored inside MI20. In this case, the linked variable is where it's going to be stored. So really, what's the difference between numeric and stream? You can use a stream if you're going to be sending number values. So say I was sending 123, I could do it with the numeric tab just like this. And I could also do it with the stream just like this. It would read in 123. If I have stream, it will also read in the words hello, say, or the words hi. If you have stream selected, it will read in either a numeric value or a number value, say 123, or it will also read in text. But the main difference, if you are sending a number value, something to consider is that when you have the stream tab selected, it's going to store that number value, say 123. When you select stream, it's going to be in the ASCII equivalent value. So we have MI20 linked here, and if I send 123 with stream selected, it's going to send 123, but that 123 is an ASCII decimal. So what you need to do is convert that from ASCII to a numeric value. We have a function for that, but really if you're sending a number value and you want to actually work with that number value somewhere in the code, it's best to use numeric. So let me just recap that because it is a little confusing. If I send the value 123 and I have numeric selected, the actual value inside MI20 will be 123. If I send 123, it will actually put 123 inside MI20. If I select stream and I send 123, it's going to store the 1 as an ASCII character, the 2 as an ASCII character, and the 3 as an ASCII character. So it's going to be the ASCII equivalent. And just in case we forgot about that, the ASCII equivalent, I have that in my PowerPoint. And we'll go through the ASCII table. You can see a 1 is equivalent to a 49. So if I just send the value 1 with stream selected just to simplify, there'll be a 49 inside my linked operand. So if I have numeric and I punch in a 1 and send a 1, there'll be a 1 in the register. If I have stream selected and I send a 1, the ASCII representation of the 1, which happens to be a 49, is what will be contained inside the register. So if you're using numbers, really it's best to use numeric. You can use stream. It will give you the ASCII equivalent value, and we do have function blocks that will take that ASCII value and do it for you, but essentially the numeric tab does that function block for you already. There's no need to have extra code to convert from ASCII to decimal. It does it for you when you select numeric. But let me explain a little bit about the stream's definitions anyway. So you have the link. The link value here happens to be MI20. So the string that we send, the string will be starting at MI20, and it will be storing it in the next consecutive register. So MI21, 22, 23, depending on the length of the string. As we saw before, each MI can hold 2 bytes, so each MI can hold 2 ASCII characters. The first 2 are stored in MI20, the next 2 in 21, 22, 23. That's how the vector is defined. That's how the memory allocation is set up if you have this example program the way I have it. Vector length, that really just tells you the maximum number of vectors to reserve. So if I have 15 as the length and I have 2 characters for each, I can have a maximum of 30 characters spread across my 15 different memory integers. So when you select 15 with a vector length, it's going to reserve MI20 through 34, I guess, is what it would be. So the vector length, how long your string is going to be. Now, one option you have under the next drop-down is convert 1 received bytes to 1 linked element or 2 received bytes to 1 linked element. Now, I just explained that you can have a total of 2 bytes inside a memory integer. Right, each character contains 1 byte. If you wish, you can do convert 1 received byte to 1 linked element, so you'll only be storing 1 character in each memory integer, but the maximum size of a memory integer allows you to store 2. So really, if you're using a memory integer, it's generally best to select convert 2 received bytes to 1 linked element because a memory integer is 16-bit, therefore it can hold a total of 2 characters inside that memory integer. And just as a note, you'll see if I happen to pick a memory long, so say I pick memory long 20 instead, you'll notice I can still pick convert 2 received bytes to 1 linked element, but really with a memory long, that is a 32-bit register, so we can actually, as we saw in the PowerPoint before, we can fit 4 characters or 4 bytes. So when memory long is selected as the link, you'll see 2 more options open up now. We can convert 3 to 1 linked element or convert 4 received bytes to 1 linked element. So a larger register lets you hold a total of 4 characters like we saw before. Function block also adapts to that depending. I have 4 options now with the memory long. If I change it back to MI20 instead, the max I can do now is convert 2 received bytes to 1 linked element. So really, we recommend generally that you would do the maximum amount of characters stored inside the memory type can handle. Select that maximum type. It just gives you better memory utilization. And what happens if you pick a lesser value? So if I pick, say, convert 1 received byte to 1 linked element, it'll just store that the J from July in the first register, the U from July in the second, MI21, say, the L in MI22, so on and so forth. But what it also does, it stores, say, the J in MI20, it'll put a null after that automatically. So the character, the 1 byte, takes up essentially half of the memory integer. The second half of the memory, the reserved space, is just filled with a null. So that's also true if you have 1 received byte to 1 linked element in a memory long. You'll have the character, and then you'll have essentially 3 open spaces. It'll just be empty space and null is inserted to occupy the rest of that available space inside the actual operand type. So in this example, we did convert 2 received bytes to 1 linked element. Also, if you're displaying this out on the screen, it's really best to do the maximum value. I'll explain that later. But generally, as I mentioned, you should utilize the maximum space that's available inside the operand type. So whether that's 2 for a memory integer or 4 for a long or a double word, that's generally the best practice to go ahead and do. There's also a checkbox if you want to go ahead and add a null to the end of the stream automatically. If your device doesn't send that, you can have that be added to the variable via this function block. And also, if your stream is going to be a fixed length, the checkbox is there for that as well. Typically speaking, we would not have either of those selected, but again, there's times and purposes where you may want to have each of those picked. So the last tab we have is the checksum. So certain devices, they will actually send a checksum. And what is a checksum? A checksum is kind of It's kind of an integrity test, I guess you could say. It's a common practice in a lot of applications, whether you're coding in, say, like C++ or any other language. Generally, say an executable file will have a checksum. A checksum really just verifies that the code is actually a valid message that's been sent back and forth. Different devices will have different configurations, I guess you could say, for the checksum. There's different calculation types, where the sum8 or CRC is another common one that's used a lot, CRC8 or CRC16. Basically, we support a bunch of different types of calculation types for a checksum if your device requires it. A lot of times they won't, but if your specific device requires a checksum, the main idea is that we do support the ability to add that into your string. If your third-party device does require it, we can pick the calculation type and the different specific parameters. So really these would just match to your third-party device if it does indeed require that. So that was the main idea for adding a variable. What else is going on in this protocol scan block? In this particular application, we just had the one variable to receive the message sent from the terminal. You can also go ahead, you can insert message before, insert message after, append messages, delete messages. Basically, you can have multiple different types of strings that you're reading in a single scan block. When I go to add a message, it asks if I want to make sure and add one. It'll increment the pointer. I'll click OK. So if your device is going to be sending multiple messages, say you have a device that sends the word off, and then you also have one that sends the string on. Instead of using a variable like we have, I'll delete that message just so we can see. You can have static text defined as well. So the device sends off, it will receive off, and what you can really do, you can do ladder operations based on the message that's been received as well. One way to indicate what string has been received, you'll notice the last parameter you can define is the index of message received. So if we have a device that sends the word off as a string in all capital letters, that's received. MI2, which we happen to have defined as our index of message received, that will contain a 0. If the third-party device sends a 1, it will then hold a 1 inside that MI2. And we can use, say, a comparison statement or some other type of logic to go ahead and do some external operation, whether that's setting a bit, turning an output on or off based on the string that's received. That's one way that you can go ahead and use the static messages and the index of message received to have an idea for what's being sent and perform some logic based on that. I mean, you can also have this in conjunction with a variable. Really, the main point, though, is that this protocol block, it is user definable, it's open, and you can essentially make it so that it will receive whatever type of ASCII string your device is sending. We allow you to do that pretty well with the option for the variables and typing in the static string, whatever it happens to be. So a couple other things in the function block as well. If your device sends a start of text, we support that. So say your device, before it sends the word off, it goes ahead and sends a $sign. So certain devices will have certain control characters as a start of text before a valid message is sent. It'll happen to include a $sign. You can just go ahead and pick that. Sometimes it'll have 2 or 3 or 4 control characters as start of text. You just double click, open up, and whatever one it sends, you can essentially pick. The ASCII to hex table is more or less inside this block as well. It matches that lookup table that we saw inside the PowerPoint earlier. So you can match your start of text. This will, when you have the checkbox selected, it'll place it before every single line that you have defined in the scan block. So if you have 5 different messages, it'll automatically place your start of text character before it. If your device happens to send different control characters, different start of text before each type of message, so if before the word off we send a different type. So you can right click. I just added a space here is what I did. Before it was off, I hit the space bar. So I have an empty character here. I can right click on that and do add control character, and I can pick, say it sends a hash sign before the word off. Now I added that specifically only to that one line of string, and before on I'll add a space, right click, add control character. Let's say before on it sends a % sign, and I'll hit OK. So this allows us to have a different start of text, a different control character before the word off and before the word on. You'll notice this one we had selected a % sign. That's showing as a 25 on the protocol message. I'll scroll back down so you can see. Really, a 25 is the hex representation of that ASCII character. So the ASCII character it's sending is a % sign. Really, the controller just interprets that as a 25. Same is true for any of the control characters or also any of the text that we looked at earlier. We looked at before high was 48 and I was 49, so we had 48, 49. Same principle applies throughout the control characters. For the most part, you don't really have to worry about that because we will always give you somewhere in the program that correlates it, or you can always just look online too. So that's our start of text. As far as the terminators, you do need to specify some type of terminator, whether or not there's 3 options here, whether or not that's a silence duration, a message length, or an end of text. For simplicity, we had just selected silence duration for this example program. So what happens when you have silence duration selected? That will wait and see. So a message is sent. If there's no other message sent after 10 milliseconds in this case, it will go ahead and process that. It'll register that message as being received. So if you don't know the control character and end of text, or you have a varied message length, silence duration is a good general option you can select after a message has been sent. Nothing has been silent, nothing has been sent for 10 milliseconds. It'll go ahead and accept that message as one that has been sent, is what the silence duration actually says. If you only have a single string and it's always going to be the exact same length, you can use the message length as a terminator, but it's important to note that this message length is going to apply to every single line that you've defined in the scan block. So if we selected, say, 3, or let's say 4. If we picked 4, it would accept the first message that we have here, our index 0. However, it would not ever accept our index 1 because that is actually a length of 3. So if you have varied length strings that you're sending, really the message length would not be the best option to select. You'd want to use, say, silence duration, or there's also the option for end of text. So a common end of text that a device might send is, say, a carriage return. So we have the option to select that. Carriage return is a 0D. We could pick that. A lot of the times they'll send carriage return line feed. You just select the length as 2, and I can define my first end of text as a 0D, a carriage return, and my second end of text as a line feed, a 0A. So now, whenever a message is sent, we have our control character of a hash sign, the word off, and then the device would have to send a 0D, 0A, which is a carriage return line feed for the message to be successfully accepted, is really what the end of text is saying here. Same principle applies as the start of text. It will insert the end of text to every single line in your message definition here. If you do, for some reason, have different end of text for each character as well, like you did with the start of text, you can just pick the silence duration and go ahead, right-click, add a control character, and manually add the carriage return to each line. So really, you can define it to be whatever your device is sending. The three different indicator operands that we define. We talked about the index of message received. If it receives off, it'll be a 0 as the message index, a 1 for the second line, so on and so forth. That's the index of message received, just a memory integer that we define. There is also a session complete bit. The session complete bit will go high whenever you send a message. So a message has been sent from the device, it's received on the controller. Once it's successfully received that message, it's scanned, it received the message, that session complete bit will go high. Now it's important to note that that session complete bit, it will not go low on its own. It does require a manual reset. So you have to have some sort of logic after you receive a message to actually reset it. It'll go high on its own when a message is received, but it does require some logic to actually go ahead and reset that so that it's actually a valid indication the next time a message rolls around and comes into the controller. Number of bytes received. This memory integer, generally you don't use it quite so much as you would the other two, but the number of bytes received will just tell you the length of the message. So if you send a message into the controller scans, it reads it, and reads the word, say it reads the word on, that's going to give you 2 bytes. A 2 will be inside MI1. If you send off, that's actually 3 bytes, 3 characters. Each character is a byte. There'll be a 3 inside that MI1 in this case for the number of bytes received. So that's really all of the parameters that we can define inside our protocol scan block. I guess the one other thing I failed to mention was select name. Here it's not so important. We only have one COM port defined. However, if you have all three COM ports have 3 different barcode scanners hooked up to it, you will have to define a protocol scan block for each specific port that's coming into the controller. So really this drop down, if you had say 2 devices hooked up, you could pick your ASCII 1 or your ASCII 2, your barcode 1, barcode 2, whatever you define the name as in the protocol config block. That's what's available from the drop down here. It lets you differentiate between the different COM ports, the different devices basically that are hooked up to the controller. You can select that from the drop down box under select name. So we're scanning whenever the receive is ready. We're scanning the messages. The next network 3, you'll notice we have a positive transition of the session complete. So the session complete MB4 is what we had just previously defined inside the scan block. So once we receive the message, this bit will go high. We will go ahead and reset our buffer so that we don't have leftover data. Next time a message comes in, we reset the buffer. And then it's also a good time to go ahead and reset the session complete. So this 2-net structure here is another common practice that you can implement when you're using protocol scan. Right after the scan block, have a net with the session complete, positive transition, reset the buffer, and then also reset the session complete so we know next time a message rolls around, a valid indicator. We can put even a counter at the end of this here to keep a running count of whenever a message has been received. The session complete is a good way to base an indicator for the messages received with that bit. Tie an incrementer to it. You have a counter there to tell you how many messages have been received on the serial port. So nets 4 and 5. Nets 4 and 5 are what we're using to send a message out of the controller. So 2 and 3, we're receiving a string into the PLC. Nets 4 and 5 are sending a string out of the PLC. So we have our MB1 send string. We'll see in a minute. This is really just the big blue button I had on the bottom of the HMI. That's what I was pressing. It had a touch property linked to MB1. It was therefore telling us to send the message. So if you've been tuning into any of our webinars or have looked at any of our previous examples as well, you'll notice this 2-net structure is something we recommend whenever you're trying to do any type of communications, whether it's Modbus or anything else like that. We recommend this 2-net structure where you have a positive transition from, say, a button on the screen. It sets a bit. That bit then go ahead and enables the net right below it. So why do we do this 2-net set and hold structure? I'll just briefly recap. We do it so that in case a message is being sent already, essentially if the COM port is already being utilized and we try to send a message, if we just have the positive transition tied directly to the send block, it may miss that. It may not actually send the message. If the port was busy, we only have a one-shot telling it to send, it may just miss sending that message. However, when we do have this 2-net structure, it allows us so that it's going to see the button press, the one-shot, set the bit, and it's going to keep trying to send it until this function in progress is no longer busy. Then it'll send the message. So really, we're making sure we send the message regardless if the COM port is busy at that exact instance when we had pushed the button. It gives us some breathing room, essentially, to make sure we don't miss sending a message. So open up the protocol send block. And you'll notice it looks extremely similar to the scan block. I won't go through all the variables and everything and such, but essentially it's the same as the scan block. You can define your variables with the create new add variable, your start of text, end of text. We happen to have a control character here, the 0D, which is a carriage return. I've added that to the line. I guess I'll show you real quick if we add the variable. There's a couple other options here which are cool too. If you want to send a message based on the value of a bit with the binary text, so say we pick MB5. If MB5 happens to be low, instead of just sending like a 0 state and MB0 is low, we can say turn on heater. And if MB1 or MB5 rather is in the 1 state, if it's high, we can send the message out turn off heater. So really we can just send a text message based on the value of a bit without any extra function blocks being required. Yes, you can do this by logic, but it'll take a couple nets to do. This protocol send has it built in to this variable that you assign, so it really just makes it a lot easier. A lot less coding. Numeric, we saw that's pretty much the same. Nothing more really to explain about numeric or stream. List of text, these are also features that's available on our HMI, but it is built into this protocol send variable as an option as well. What you can do is define a memory integer, say MI6. If MI6 happens to contain a 0, we can send out the text 0, say. We can add a string. If it's a 1, send hello. If it's a 2, send bye. Really, it just lets you send a message out of the serial port based on a numeric value that is currently contained inside a numeric integer register. So it has its uses. Checksum, again, we saw that before. You can add the checksum to the end, but two other new options are the date and time. So again, you can do this via the ladder relatively easily. However, it's much easier just to do it inside the send block. You can send the day of the week, a 3-day day, day, month, year. Same is true for the time, hours, minutes, seconds. There's no extra ladder code in the logic required to do that. Yes, you can, but it's a lot easier just using the protocol send variables that are built in. One last option in the send block that we should talk about is, is the Advanced tab. Inside the Advanced tab, there's a checkbox to send data destination. So what this allows us to do, when whatever memory bit we assign is on, so if MB6 is high, it's on, we're going to copy whatever messages we're sending out of the protocol send block, and we're going to copy those to a section of memory. So we're going to copy whatever message we send, say, out to MI1000. And once again, 1 character per register or 2 characters per register is all it's saying. So it allows us to store this in some other portion of memory, and then we can, if you want to log that to a data table to have a record of all your messages that are being sent out, it's one example of why you may want to do this. And that's really all that there is to say about the protocol send block. We'll look briefly at the HMI. You'll notice my MB1 is the touch property for my send block that we had just looked at. MI3, I guess I didn't say this, but it's pretty clear. There's just an incrementer on here. MI3 is incrementing whenever we're sending a message. So we send a message out, increment MI3, and we just happen to be displaying that on the screen here with a variable numeric. Now, the ASCII block is something worth mentioning. Under this text header, under the center pane, you'll notice where my mouse is right now, there's an ASCII string variable. It's the # with a red dot and an A. That's what I have drawn out on the HMI right now. If I open that up, we can take a look. Things that you need to define inside the variable ASCII string. This variable ASCII string, first let me say, it just allows you to display a vector of ASCII characters in human form so that you can actually read them. So we have, our hex values are 49, 48, 47. Our 3 characters are stored in MI20 and 21, say. Instead of just displaying those numeric values that don't really make much sense to the average person, you can use the variable ASCII string. So all we need to do for that is point it to the start of vector. So we saw it in the scan block prior in our network that MI20 was the linked variable. So MI20 is where, in this case, we're storing whatever message is sent into the controller. So when I was sending hello webinar to this screen before, it was storing it inside MI20, 21, 22, 23. MI20, though, is the start of vector address. That's what you need to define as the first parameter in this ASCII string block. You can also define the maximum number of characters. So this is really just allotting enough space for the HMI display. I have it on 30 right now. You can see it says text to display, text to display, text to display. If I make this only 10 characters, it'll just chop down over here the maximum number of characters it'll display on the HMI. The string pattern here is really pretty arbitrary as well. It's only for the display inside Physiologic where you'll actually see it. It's not any real bearing on the actual application itself on the PLC. If I change this to JSON, it'll just show you that repeating on the screen. I guess if you have multiple strings, you can have it like barcode 1, barcode 2, barcode 3 for your different variables that you're trying to display. Now, the other thing we need to define here, last parameter, is the link. So the link, I happen to link this to our session complete. What this link actually does, it's a little confusing compared to the nomenclature for our other blocks, but the link here is just linking it to a refresh bit. So it's not really quite so relevant for the color screen controllers, the enhanced color controllers, or the 130, say, even that we have right now. It's more of a legacy bit. The older 120s, say, or the 200 series, they require that you refresh the screen before a variable string will update. So if we sent hello and then webinar on, say, a 200 series controller or a 120, you would have to manually refresh the screen for it to actually update and show that that new message has been arrived. So the way you would do that would be with assigning a memory bit here to the link, and you'd pulse that somewhere in the ladder logic, typically to the session complete bit, which is why I just did it here anyway, but that would refresh the screen. Really, it's more just of a dummy bit on the 570, say, or any of the color controllers 130. I put MB 1002, and even if I never pulse anywhere in my logic MB 1002, it won't matter. The screen will still update on its own. It's just handled by the operating system essentially now. It was added to the features for the color screen controllers, the operating systems for those enhanced controllers, so that it automatically updates the screen for the ASCII variables. There's no need for it. However, if you try to not define it in the ASCII string block, even on these color controllers, it'll yell at you. It'll make you define one. So you even if it's just a dummy bit, one you'll never use in your application, make sure you define the link. But really, don't get it confused with the start of vector. The start of vector is where the string, the actual information, the character that you want to display on the screen. The start of vector is where you specify that. The link in this ASCII string variable just happens to be a link to a refresh bit, which is legacy for the newer color controllers. Only other thing here really to say is the keypad entry. If you want to make it so that the user will type in a string on the screen, you click the keypad entry. When the user clicks that variable, it will open up a alphanumeric keypad, and you can go ahead, type in a string. You can save that to a memory vector location, link that memory vector location to a variable inside your send block, and you can send out a string that the user typed on the screen. It's relatively easy to do. It's just another option that we have with the ASCII string block. So that's pretty much all there is to say about the actual application. I will mention one more quick thing though. A useful tool that we have is the memory tool. So by default, you should have your operands open on the bottom left here, the salmon colored, displaying the different bits and whatnot. There is a tab on the bottom for memory. Now this is a very useful tool for debugging when you're trying to work with strings. Memory actually will allow you to see the ASCII representation of your characters without having to have a display variable on the screen, say. So let me just fire this back up. I'll go into online test mode, and I'll open my Hercules connection back up as well. Let me just clear the screen, open back up. Alright, so let me bring this so you can see it as well. Okay, so I have nothing on my receive screen right now. If I go ahead and send webinar, it pops up on the screen. It's storing that inside MI20, right? That's what we had just seen from the scan block and also our HMI variable. It's stored in a vector starting at MI20. So we can go ahead and look at that. If we're on the operands tab, I will go to memory integer, go to MI20. Alright, so we see all the space reserved here for the message. Now it's really not so useful. Like, what am I seeing here? 25943, what does that mean? It's in decimal format. It's representing this string webinar. Way to make it a little bit more useful, if I double click, it'll show the hex value instead. So when you have it open as hex, you can see the 6.5, the 5.7, those each two pairs here are actually corresponding to ASCII variables. So if I look, let's look at what's a 5.7. A 5.7 in hexadecimal should be our W. So we have our W, so on and so forth. Webinar is what will be displayed out. Now really, a normal person can't read that. There's no need to memorize it. So what we have as a tool under the memory window, you'll see right now, I defined, I'll just re-add it so we can see. Let me clear that. What you need to do is click on memory, right click. You can add as many rows as you want, but once you click the first row, the browse box will pop up. It's pretty easy to do. Just punch in, I want MI20. My length, let's say our length was 15. And it should be on ASCII by default. So if I open that up, you'll be able to see that, I don't know why it's down there still too, but MI20 is showing the ASCII string as webinar. What I can also do, which is cool, is I can make it back to hex. You'll see now the hex equivalent for each of those characters. So the 6.5, the 5.7, the exact same thing we're seeing displayed out in MI20 through 23 here is also being displayed in hex. However, decimal, again, not so useful, but I can put it into ASCII, which is what is really useful to see the string that's coming into the controller. So that was the main point I wanted to make. You can use this ASCII tool, and you can go ahead and see what message is being included in the controller. One last thing that I can't really show you on my controller because information mode is not supported inside of remote access. However, if you're following along right now with a controller, if you have one on your desk, say, and you know how to enter information mode, you hold your finger down on the screen for 4 seconds as the default time. It will ask you to enter an info mode password. Default password is just 1111, so 4 number ones. Inside information mode, there'll be a tab for serial. And then inside of serial, you'll see on the bottom right-hand side, there will be a tab for monitor. So monitor is also an extremely useful tool for debugging your serial applications. What the monitor does, you'll see if you have the controller in front of you. Again, I can't show you this, but on my screen. However, there's a TX and an RX. This serial monitor will actually show you the raw string that is being sent into the controller and the raw string that's being sent out of the controller. Again, that's just in information mode. It's the serial tab, and then monitor is on the bottom right. But that will show you the string that's coming into the controller. So it'll show webinar, or it'll show, send test message for this particular example. But even if your protocol scan block is set up incorrectly, this is the important part. If you didn't define your protocol correctly, it will still always show, regardless of your code, what the message is coming into the controller. So it really kind of bypasses your code and will show you the raw value that comes in and out of the controller. So if you're trying to figure out why your device is sending a message, and you know the device is sending it, but your controller isn't reading it, the session complete bit isn't coming on, you can check the protocol serial monitor to see if, in fact, the device is sending it. If there's any hidden control characters that are being sent, you can toggle between hex and ASCII on the bottom right-hand side of the serial monitor as well. It shows you a message count. So I just wanted to point that out as well. It's an extremely useful tool. It lets you do it for ports 1, 2, or 3, selectable on the top right-hand side as well, to monitor your different COM ports. So that's really all that I wanted to cover for the duration of this webinar. I'd like to thank everyone for attending today. If you have any other questions, we will leave the webinar open for a little bit. You can go ahead and send those to the questions window. Also, any follow-ups can be sent to support@unitronics.com. If you have any general questions, suggestions, feedbacks on how you think the webinars are, sending it to support@unitronics.com is always a good place for that. And also the recorded version of this webinar, along with all of our other previously recorded webinars, are available online in 2 places actually. If you go to www.unitronics.com/webinars, it'll bring you right to our forum page where you can find all of our recordings. And also if you're on the Unitronics main page, it will just be unitronics.com. There's a support tab, and then there's also a sub-tab for webinars. You'll find all of those up there as well. So you have those 2 places to go back, check out the resources, the application file from this webinar, as well as the recorded video, and the PowerPoint will be available online. So once again, thank you all for attending.